In this video, we're going to do some sample problems using the formulas for pH and pOH. Let's go to our handout to try those practice problems out. You'll need your calculator because you want to practice using the log function on that calculator. So we'll start off with the first examples here, example A and B. We want to determine the pH of the following solutions. So we have a solution with a hydronium concentration of 0.001 moles per liter. So our formula would be the negative, so pH is equal to negative log of H3O plus, which is so negative log of 0.001. So you would go in your calculator, hit the negative button, not the minus button to subtract, but the negative button to make things negative. So we do negative, hit the second function, log, and then afterwards, I usually put my concentrations in brackets. You don't necessarily need to, but I do anyways. And I put open brackets, 0.001, and I get a pH of 3. So try that on your calculator. Make sure you can figure out the log button on your calculator. Let's try this example over here. So we have, actually it's the same example. What we'll do is we'll change this up a bit. We'll do, instead, I will give you the pH, and you will come up with what the concentration of the hydronium ion should be. So if I say you have a pH of 4, so remember that if you want to find the concentration of H3O plus, you would simply do the 10 to the power of negative pH, which is 10 to the power of negative 4, which is, so you do your 10 to the power of negative 4 in your calculator, and you get 0.0001 moles per liter. And that would be moles per liter because it's the concentration of the hydronium ions in the solution, and it's a molar concentration. Let's do another example similar to that one over here. So determine the hydrogen ion concentration of a solution with a pH of 6. So let's go ahead and try that out. So we know that the concentration of hydronium ions is equal to 10 to the negative pH, which is in this case 10 to the negative 6, which is, so 10 to the power of negative 6, 0.000001 moles per liter, and that's the concentration of hydronium ions. Let's do one more where we have to find the pH from the concentration of H3O plus. So here's H3O plus here. Let's say the concentration is 0.056 molar. Try to find the pH, so you can try it out yourself, and then I'll put the answer there. So our log of 0.056, and we get about, keeping it to the same number of sig figs, 1.3. So there were 2 sig figs here. I had about, in my calculator, 1.251811973, but I kept it to 2 sig figs. This is a 5 after the 2 plus a whole bunch of other numbers, so it's past the midline. So pH of 1.3, which is quite acidic. Of all the pHs we calculated here, it looks like the most acidic one is the 1.3. So that was just some examples of using the negative log of H3O plus to calculate pH, and then to go from pH to the concentration of H3O plus as well. But sometimes we might provide you more of a word question to do. So let's do example C over here. Determine the pH of a solution with a hydrogen ion concentration of 0.25. So the answer is here, but let's see if we can figure it out, and you can try to get that answer as well. So we want to find the pH, and we know the pH is the negative log of the concentration of H3O plus or H plus, which is in this case the negative log of 0.25. And so let's do our negative log of 0.25, and I get about 0.602059991. But to keep it to 2 sig figs, I'm going to do 0.60. And that's my pH. Quite acidic, below 7, much below 7. even below 1. So again, based on the pH, you can tell if your solution is acidic or not. Let's try the next example over here. Determine the pH of a 0.0015 molar solution of hydrochloric acid. So be careful here. In this question, we told you the hydrogen ion concentration. In this question, we're telling you the hydrochloric acid concentration. So remember, that's HCl. So I'm writing down an ionization equation. Aqueous becomes H plus, and it's a strong acid, so I do a single arrow. Aqueous plus Cl minus. Aqueous. And we're told the concentration here is 0.0015 molar. Now I make sure it's all balanced, 1, 1, and 1. And because they're all 1-to-1 ratios, these concentrations will end up being the same. So concentration here will be 0.0015 molar. And same thing with the concentration of Cl minus. We don't really care about that because remember the pH is based off of the hydronium ion concentration. So if there was a 1-to-2 ratio, I'd multiply by 2 to get the 0.0015, multiply by 2 to get your concentration of H+. So whenever you're given not necessarily the concentration of the hydronium, hydrogen ion concentration, but instead of the acid or the base, you have to do your ionization or dissociation equation to find the concentration of the H+ or the OH or whatever you're dealing with. So now that we have our concentration of H+, we can do our pH is equal to the negative log of the concentration of H+ or H3O+, same thing, which is equal to the negative log of 0.0015. So negative log of 0.0015. And I get 2.82390871, which I can say is approximately, to 2 sig figs, 2.8. So the pH is 2.8, which is still acidic. And it would make sense because it's a solution of hydrochloric acid, we'd expect it to be acidic. If you have a greater concentration of hydrochloric acid, you'd have a greater concentration of H+, and it would be more acidic. So again, here the reason we had to do this ionization equation is because they told us the concentration of the acid as opposed to directly the concentration of the hydronium or hydrogen. So we had to figure it out from a ratio using our ionization equation. So we already did the examples with finding the hydrogen ion concentrations from the solution, from the pH of the solution. Let's go ahead and take a look at how to do some pOH calculations. So determine the pOH of a 0.0015 molar solution of lithium hydroxide. If you remember, this here is a strong base. Let's write out lithium hydroxide. And so it's a solid. We're doing a dissociation equation. We're going to get some lithium over here, plus 1, aqueous, plus the OH minus, aqueous. And we're going to write down our concentration. Our concentration here is 0.0015 molar. And since it's all a 1-to-1 ratio, the concentration of everything else is the same. So we're going to have concentration of this once it dissociates 100% is 0.0015 molar. And same thing with the hydroxide, 0.0015 molar. So that's our step 1. We wrote a dissociation, and we found the concentration of hydroxide. So now our pOH is going to be equal to the negative log of the concentration of OH minus, because that's what we're dealing with here, OH minus there, which is negative log of 0.0015, which gives us, so negative log of 0.0015, we get about 2.82390871, which is approximately to 2 sig figs, 2.8. So that's the pOH. You have to be careful with this here, okay? Because if I were to ask you if a solution is acidic or basic, you're dealing with pOH right now. So pOH, think of the scale as kind of inverted. The lower your number, the more basic you are. If ever you're unsure when you calculate pOH what you're dealing with, you can always convert this to pH. And so I'm jumping ahead here, but just to show you as an aside, we know the pH is equal to the pH plus, let's erase that to make it more clear, pH plus pOH is equal to 14. So if you wanted to find the pH, you could simply do your 14 minus pOH, which is 14 minus about 2.8. And we get 11.18, roughly. Now we'd have to look at sig figs and everything too, but I'm not going to look at that right now. I just want to show you that you could convert to pH if you wanted to from the pOH, and just showing you that your pH is above 7 here, quite above 7, so it's basic. So be careful when you're interpreting if something's basic or acidic using the pOH. It's the opposite for that scale. So something lower than 7 in a pOH is basic, higher than 7 is considered acidic. But if you're confused, just convert to pH using this calculation here, and you'll get the pH, and it's higher than 7, so it's going to be basic. So let's go ahead and try this next example out over here. We have determine the pOH of a 0.0015 molar solution of barium hydroxide. So we didn't give you the concentration of hydroxide, we gave you the base. So we have to do a dissociation equation first. So we're going to have barium hydroxide, which is BaOH2. It's a strong base. It's going to become Ba plus 2, aqueous, plus OH minus, aqueous. And since there's 2 hydroxides here, we have to balance it to put 2 hydroxides there. Now the concentration over here is 0.0015 molar. We want to find pOH, so we need the concentration of this OH minus here. We have a 1-to-2 ratio. So we have a 1 barium hydroxide to 2 hydroxide ratio. So to find this concentration, because we're not changing the volume, we can just do our concentration ratios. If we're changing volume, that would be different. But right now, we're just assuming same volume. So we can just find the concentration of the OH by doing our 0.0015 molar times 2 OHs for every 1 barium hydroxide. So we're multiplying it by 2 essentially. And we're going to get, so if you do your 0.0015 times 2, you get 0.0030 molar. So this is the hydroxide ion concentration. This is the hydroxide ion concentration because we balanced it and it was a 1-to-2 ratio. Now, we can do our pOH is equal to negative log of concentration of OH minus, which is a negative log of 0.0030. So negative log. That gives us about 2.52287875 for our pOH, which is approximately to 2 sig figs again, 2.5. Oops. 2.5. So that means since this is pOH, we still have a basic solution. If you want to just make sure by converting to pH, you could simply do your 14 minus pOH. pOH is equal to pH. So that means that our pH is going to be equal to 14 minus our 2.5. So we will get about 11.5. And you can see that we are much higher than 7. So we are basic again. So that was calculating pOH from the hydroxide ion concentrations. Let's go ahead and try our last example here, determining pOH and pH together. So we have and we've already done that actually, we did it as the aside there. So here we have our calculate the pH of a 0.00048 molar solution of NaOH. You cannot calculate the pH directly. Okay, so what do I mean by that? Well, here we gave you the concentration of a base. So we have to write out our dissociation equation because I didn't give you the hydroxide or I didn't give you anything directly. We get Na plus AQ plus OH minus AQ. Now, the concentration here of the NaOH is told to be 0.00048 molar. Since we're in the same solution all the time, we're not changing volume, we can do our molar concentrate. We can do our concentration ratios. Since we have a 1-to-1 ratio, the concentration of hydroxides is also going to be 0.00048 molar. Now, with this, we can find the pOH. So that's our first step. We can find our pOH, which is equal to negative log of the concentration of OH minus, which is the negative log of 0.00048. And so we get negative log of 0.00048. And we get about 3.318758763, which is approximately to 2 sig figs, 3.3. So we have our first part here, the pOH found. So I'm just going to put my therefore pOH is approximately 3.3. And then now we're going to go ahead and try to find the pH. So our third step is finding pH. Now we don't know the concentration of H plus right now. We could figure it out, actually. There is another relationship I didn't teach you that actually can provide you the concentration of H plus from the OH minus, but right now there's an easier way. We know that the pOH plus the pH are equal to 14. So if we want to find the pH, we can simply do the 14 minus the pOH. And so we can do our 14 minus 3.318758763. And we get approximately 10.68124124 as our pH. And then we can put the proper number of sig figs. So it looks like we need to have 2 sig figs in this question here, because that's what we had to start off with over here. So if we want 2 sig figs, it looks like we can round that up to about approximately 11. Now with pHs, generally to check your work, you want to check the unrounded to see if they add up to 14, which they should. Be clear that you've rounded with sig figs here, so we know why it's not exactly adding up to 14. We rounded up in this case because we wanted 2 sig figs in the end. So I just put in 2 sig figs here and 2 sig figs over here. So it's approximately 11 because we're following our sig fig rules that are there. That there's just how you would do an example where you want to find the pH from the pOH given the concentration of the base. So you won't always be given the concentration of the hydroxide or hydronium. You would have to find it through a dissociation or ionization if it's an acid, if it's a base association. And then once you find the pH or the pOH, you can find the other by using this relationship over here. The last point I want to discuss before just concluding. So we talked about doing these problems here. These problems are typically going to work out for strong acids and strong bases. So the way we did it here with our dissociation or our ionization, where we're assuming that all of this becomes H+, that can only work if we have a strong acid or a strong base. When you have weak acids and weak bases, remember that it's not 100% going to become H+, for example. So I can't assume that the concentration would be equal. It only really is for the strong acids and bases that would work for. For weak acids and weak bases, I would provide you with the H plus or OH minus, for example. I would actually give you that. And there is a way to calculate it and to figure out, how much becomes H plus, how much becomes OH minus if it's a weak acid or a weak base. But that's something you would learn in grade 12 under the equilibrium of acids and bases concept. And the last thing to touch upon, still based on the strength of acids and bases, a lot of students think that if you have a strong acid, your pH always has to be low. And if you have a weak acid, your pH is higher. Okay. Now, that would be true if they're equal concentration. So if I have an equal concentration of strong acid and weak acid, all of the strong acid becomes H plus, so it's more acidic. It'll have a lower pH. pH is lower than a weak acid. This would be less than 100%. Let's say 1% becomes H plus. So this is going to have a higher pH. It's not going to be as acidic if you have a weak acid. But it doesn't mean that the weak acid is always going to have a higher pH than a strong acid. If they're equal concentrations, yes, that's the case. But I could take a weak acid and make it very concentrated. If I have a very concentrated solution of weak acid and a very dilute solution of strong acid, yes, all the acid H plus will become all the acid will become H plus, but it's very dilute. So my concentration of H plus would still be relatively low, even though it's a strong acid. So I want you to get that strong acid solutions don't always have to have a lower pH than a weak acid solution. It really depends on the concentration of that strong acid. If I made it very, very dilute, the strong acid would have a higher pH than the solution of the weak acid if the weak acid was extremely, extremely concentrated. But it takes quite a bit more concentration to make the pH lower than the strong acid. But I want you to get that the definition of strong acid is not low pH. It's 100% ionization. And the definition of weak acid is not higher pH, 007, but higher pH. It's really just less than 100% ionization. So keep that in mind when you do calculations. And again, just do notice that what we did here with our dissociation and ionization and assuming equal concentrations there, and we could directly kind of convert everything as is, that only works for the strong acids and strong bases, because weak acids and weak bases do not go 100%. You kind of have to figure out how much they go, and that's more of a grade 12 concept. But if you are interested, you could always go and just research a few videos on YouTube or ask some questions regarding weak acids and weak bases. That concludes our calculations for pH and pOH for pH and pOH. Now you have a better idea as to how that works. Do make sure you practice your log function.